Before we start, I'd like to thank the organizers of this wonderful workshop for the opportunity.
I think start from the beginning again.
Hi everybody, this is Chai from Cruise. Before we start, I'd like to thank the organizers of this wonderful workshop for the opportunity to allow me to speak on behalf of Cruise. And I apologize for not being in Tel Aviv in person, but trust me, I would have loved to drop by and attend ECCV in person. Unfortunately, I'm held up here in San Francisco. Today's workshop is about map-based localization for autonomous driving. However, our company has so far not published too much about our mapping strategies. So instead, I'll primarily focus my talk on the topic that has been on top of my mind for the past couple months, which is the testing of the self-driving car in simulation. However, I still promise that I'll highlight some of our ongoing work in mapping and outlining some of the challenges that we are still facing. Just a few couple words about Cruise. So we are a self-driving car company based in San Francisco. We have been in business for about 7 years, and we specialize in building self-driving cars for ride-hailing and delivery services. How are we different from other self-driving car companies? I think first, we are one of the first to operate a driverless fleet in a dense urban city, that's San Francisco, in the United States. So I know the word driverless has been thrown around a lot. Just to clarify what we mean by driverless here, so literally no safety driver of any kind in the driver's seat or passenger seat. We are not operating just in simulation. We actually have physical cars driving on the street. In fact, we have really many of them. If you drop by in San Francisco, you'll see them quite often. And our customers are not liable to damages, so we don't yield the control to the customer when emergencies happen. So we need to deal with everything that happens on the road, and we are doing it at a scale in San Francisco. Just most recently in the news, we are currently expanding to new cities, that is Austin and Phoenix. And these are relatively large cities in America. I think Austin is the state capital of Texas, while Phoenix is the state capital of Arizona. And we'll try to demonstrate that we can scale our capability fast and efficiently. Yeah, as promised, I'll first talk a little bit about mapping and with the mapping's role in self-driving and some of the challenges associated with them. Just a little bit of background on the self-driving car and then what we call autonomous driving or autonomous vehicle AV stack. Usually consists of 3 major parts. First, we have perception that converts sensory data like camera, LiDAR data into usually a kind of a representation that's somewhat like top-down, like objects and tracks. And prediction takes those tracks and tries to predict what these agents, these objects are going to do in the next 10 to 20 seconds. And then we have planning, which is about to figure out what is the next action the self-driving car is supposed to take. So usually, when you talk about this high-level architecture, you don't talk about this, but usually there are offline maps that support each of these 3 modules. So the offline maps are something that are usually also known as HD maps. These are maps that are created offline. You deliver these maps on the fly to the self-driving car stack. And the assumption here is that there are components like map components, like drivable area, like lanes and intersection logic that remain, that are persistent. Obviously, this assumption is not always true because maps can change, and we'll talk about those later. So in terms of like perception doesn't require that much map. I mean, you could supply kind of an elevation map or ground truth, where the buildings are to the perception system. But usually perception systems these days are so good that the benefit is minimal. So the only part where perception can still really benefit from offline maps is on the traffic lights, because it's part of the intersection logic of the map. So then we have prediction and planning. They rely a lot more on offline maps because they need to know where the lanes are, so we don't drive between two lanes. They need to know where the drivable areas are, so we don't drive off road, and we don't predict other agents driving off road either. And I think the most important part is intersection logic, where say you want to make a particular maneuver, you need to know which lane you need to be on, so you can do those maneuvers, for example, left turn or right turn legally. All right, I just want to acknowledge this. So there's an eternal debate about whether we should use offline maps in self-driving cars. I think some companies, they believe offline maps are necessary. Some companies believe it doesn't help with scaling of the self-driving car technology. So so the proponents say there's basically the maps, they deliver a strong prior that can help the entire stack. I mean, they think about prediction planning, and no matter how good your perception is, it's never going to deliver maps as accurate as what you can get offline, because perception has limited range after all, where an offline map has basically infinite range. But the downside of using offline maps is that maps change fairly frequently, actually more frequently than you think. And here we're not talking about like big changes, like you remove the intersection, you make a roundabout out of it, but rather the lanes, they change maybe by 10, 20 centimeters, and suddenly your map is no longer valid. And if you use the map for prediction, for planning, now you are driving off. Essentially, you're touching the lane boundaries, and they are hard to maintain. They're expensive to scale. I think at Cruise we are fairly pragmatic in terms of we are not strongly tied to either of the argument. Right now, it does seem offline maps, they have a lot of value in helping the self-driving car stack drive well. But we can also imagine a future where the components of the offline maps, which I'll touch on right after this slide, might change. Maybe we can learn some more implicit representation of the offline map rather than something that's explicitly defined by the human. Or we can one day move into a situation where there are no maps at all. We can create maps on the fly. We can create whatever prediction and planning need on the fly. So let's look at the contents of the offline map. We have obviously we have roads. So this is the first, the image to the left is showing a top-down view of a kind of part of the city in San Francisco. Excuse me. The green areas show drivable areas. The purple areas, I believe, they show the sidewalks. And we also mark where the parking spaces are. That helps us with finding places to drop off and pick up passengers. A second big chunk. So these are just the primary map elements. There are a lot of other parts that are parts of the offline. The second big part are lanes. So you want to know where the lane boundaries are. So you want to kind of you make your car stay in a particular lane and not just like go in between. think one most important part is intersection logic, as I mentioned. So you need to know which lane can turn to which other lane when you, for example, make a left-hand turn. All right, so how are the maps created? Usually, you have a data collection vehicle that's very similar to a self-driving car, equipped with LiDAR, equipped with camera, radar, and all the good sensors. And you drive in your area of interest multiple times, and you can get very good calibration in these cases, and where you can essentially overlay all the point cloud that you gather from multiple runs. And this is what showing in the picture, in the image in the middle. So you have each color is one run, and are points from one particular run. So here you see 3 colors. So you can overlay them really perfectly, and you send them for labeling. The labeling can be purely auto label. You can use machine learning tools. I think a lot of camera-based, LiDAR-based methods can already be very good. There are components which still require some level of human involvement, be it post-processing or just verification. And there are certainly also elements that still need to be manually labeled, from ground up. So, in terms of auto, we do a lot of auto labeling these days for offline maps. For example, for stop signs, it's very easy. The signs are easy because they're designed to be easily recognizable. Roads are fairly okay too, because today's segmentation methods, both in camera and LiDAR, can be very, very good. The lanes are also easy to detect because the lane markings are created to be easy to detect. Sometimes the challenges here are that the lane times can sometimes be kind of ambiguous. So sometimes you have dotted lines and you have solid lines, and maybe due to kind of old age of the solid line, it becomes kind of dotted line, and you have kind of infer what it is. So, and sometimes the colors, the yellow line, I don't know. Maybe this depends from country to country. Actually, in the US, it even depends from state to state. Sometimes the yellow lines, white lines, they have different meanings. Sometimes they don't. And again, here, intersection logic, you essentially need to know which traffic lights controls which lane, and which lane can go where, and maybe left turn, straight, right, or U-turn, and how are the traffic lights associated with them. So all these things can be auto-labeled to some extent. So what are the remaining challenges, though? One big challenge is in the precision. I think when you look at a state-of-the-art object detector or segmenter, usually when you look at COCO, for example, the object detection accuracy is measured at 0.7 IOU. And that kind of precision is simply not good enough for the map, for the quality that we need for offline maps. So it has to be centimeter precise on the boundaries, because just a little bit error will cause problems in localization. And then if you don't know where you are, you're in bigger trouble. I think another challenge is in confusion between intersection. I think intersection logic is still very hard. A lot of times you don't really see the arrows on the ground because they're occluded by other vehicles, and you have to infer the flow of the traffic from how the other vehicles behave. And sometimes traffic lights overlap each other too, and suddenly you know how in computer vision it's kind of hard to count still, right? So you have 2 traffic lights that are very close to each other. Sometimes the entire system gets confused. Right. There's another kind of big challenges related to maps, and that's construction zones. I think every self-driving car company must have some kind of a team inside to deal with construction zones, because cones and construction zones, they are fairly temporary. They can stay for as short as a few minutes or stay as long as like years. However, yeah, because they are temporary, you cannot use like offline maps as we do for lanes and drivable areas. And instead, you have to predict those, handle those online. And let's look at a few cases of construction zones and cones and see why they're so hard. So the cones themselves are not hard to detect. So cone detection these days can be very, very accurate. So that's just not really amazing. And the localization, the 3D detection, 3D detection accuracy of cones are extremely accurate. However, the challenge here is to make sense of what it means, what these cones are trying to tell you. In this case, in this first picture I'm showing you, basically there's some kind of area that you don't want to enter. So it basically marks the perimeter of an area that you should not be entering. However, sometimes people are a little bit lazier than that. They just put, in this case, it's just to put 2 cones on this right turn lane, indicating that the right turn lane should not be entered. So, I mean, this kind of logic is not something that you can just program by hand because there's so many exceptions. And here to the human, it's kind of clear that you don't want to enter the right-hand turn lane, but to the self-driving car, to the algorithm, it can be fairly challenging to recognize that the blockage applies to the entire lane and not just the area between the 2 cones. Sometimes the cones can also mean that the entire street is blocked, and you should not be kind of find shortcuts to still enter that street at all. And finally, if you are not careful with cones, and in this case, you have a big hole between the cones. So if you don't handle cones well, you'll drop into the hole, and that's not something you want. All right, so you might say, hey, yeah, why don't we just avoid all cones? We see cones and we just turn around. It's not that simple because cones can also serve to channel roads, to create new roads that you have to enter because maybe you are already, there's no way to make a U-turn and you have to follow you are supposed to follow the cones, right? So that's very challenging too, because sometimes it's about, okay, you should drive on the left hand of the cones, sometimes it's on the right hand of the cones, sometimes on both sides of the cones. So just recognizing what the cones mean and to correctly mitigate those is a big challenge. Right, so much to mapping. Hope I have highlighted a bit about what's the mapping's role in the self-driving car and what are some of the remaining challenges. Let's move on to the next topic. As mentioned, this is something that I've been personally looked at and has been top of my mind and close to my heart for the past few months. Yeah, let's start with some background. So traditionally, the self-driving car is tested on road. So say you have a new stack, you put that stack on your car, you find some safety driver, and you kind of drive around, right? In either a targeted area or a constructed setting, and where you want to test along a particular dimension. Then you measure the frequency and severity of near collisions or actual collisions or disengages, and you compare your metrics against previous versions of the same metric. But as you can see, there's many problems with this type of kind of on-road testing. First, it's slow, right? It takes weeks to get. I mean, here in self-driving, we're all dealing with long tails, and how often do you find a long tail on the road by doing road testing? So you have to. There's a long lead time until you find something. And this is a kind of very problematic for making iterative progress that we all do as machine learning engineers and researchers. And imagine like in ImageNet took, for ImageNet evaluation, you will need to hire waiters every time you have a new you want to evaluate your new algorithm. And I would guess that would not have made such progress that we have had over the past 10 years, if that were the case, right? So for ImageNet, you just run your algorithms and evaluation is like, five seconds or 3 seconds, and you get your number. And the second problem with on-road testing is high invariance. You don't know what, because between different runs, you have different conditions. Maybe the second run is on, it's almost Halloween, right? Where everybody is dressed like dinosaurs, and suddenly your perception system starts to fail. And that's not because your perception failed. Like there was a regression on your perception system, but rather the condition of the environment has changed. And that's something that's very difficult to factor out when you do road testing. So the variance is fairly high. So even if you use the same stack, you test it twice, you get drastically different numbers. And what do you do with them? So basically, essentially, you can't measure progress nor regression really well. So the hope of the community is to somehow test the self-driving car in simulation only. So you can use logged or constructed scenarios, and you can simulate from either raw sensor data or an abstracted level, like a perception outputs that tracks of other cars and other agents. And you have to control them as well, right? You can make them on rail, which means that they just, you make them move the same way that they were in the log, but without reacting to your different policy of the self-driving car. Or you can have some more intelligent counterfactual agents to represent other users. So I think the current paradigm is to shift to more and more testing in simulation because on-road testing has high latency, high variance, and it's very costly. I think this is what a lot of self-driving cars companies are currently working on. However, testing simulation is still very challenging because the environment, you have to model the environment, which means you have to model what other agents might do now that your policy has changed. Essentially, you have to train a world model. And it's not just finding one possible future for what other agents might do, but it's about modeling the entire distribution over them, right? A lot of times, if you model other agents as the polite agent, the most likely agent, then bad things are not going to happen. So you have to find the problematic road users, and you also need to know how likely they are going to happen. A second problem is you need to be able to sample from your scenarios efficiently. So if you just do kind of sampling according to the distribution that you've modeled, then you'll waste a lot of resources, right? Just by running your simulation against the most likely scenarios, but nothing ever happens in those scenarios. So essentially, it's wasted effort. And finally, metrics is very hard because sometimes it's difficult to aggregate them, and it's always hard. All right, so I just wanted to introduce a kind of one framework of, it's a very complicated problem of simulating, testing in simulation. So I therefore just want to introduce like a very high level framework and highlight how we are thinking about this problem of testing in simulation. So first, we need to find a state space, and which means we need to know what are just like a representation of the scene, right? And the secondly, we need to know what is the probability of that scenario or that state occurring. And finally, we need to be able to sample efficiently from this distribution. So on the right-hand side, I have a kind of a plot to say you have like a few dimensions of your state space, and you can now map your kind of previous observations or basically your log onto that space. And you can extract some probability densities, and you can kind of then sample from those cases. So there are long tail cases are kind of far away from the rest of distribution, and so on. All right, so let's just for simplicity, let's think of simplified 1D space. So say if your self-driving car drives in a line, and the self-driving car is on the track, it can accelerate and decelerate, so can the other agents. And for simplicity, let's just consider we're measuring the probability of collision. Obviously, usually we consider a lot of other factors, metrics like for instance safety or near collision or collision severity. These are all part of it. And we define the state space as the kinematics of all the agents, including the self-driving car and their driving policies, right? So if we have all these, they kind of uniquely define what will happen in the future. I mean, the driving policies can still be somewhat stochastic, and you have to then marginalize over the stochasticity. So now our goal is to measure the probability of collisions over the state space, and essentially it's a mapping from the state space S to like a number between like a scalar between 0 and 1. Okay, so obviously things are a lot more complicated than that, but let's assume right now we have 3 agents, and the state space essentially consists of their relative distance to the self-driving car, their velocity, their acceleration, and their driving policy. And I'm a little bit vague with driving policy because that's something I will look at in the following slides. Now, what we want to do is to measure the probability of collision to given the vector. So essentially, the vector dimension are the agents of these 4 elements and map it to 0 and 1, and that's what we want to predict. So the driving policy is the hard part, because essentially that's something that we need to learn, and we need to, that's where progress needs to be made. So even in this 1D case where the control or the action is simply accelerate or decelerate, it's still fairly complicated. So the driving policy here defines, takes the history of all the other agents and everything they observe, and they predict their next action, right? They sample their next action. So essentially this is the way we model it becomes a Markov process. And we, as mentioned before, if we know the policy, if the policy is deterministic, then the outcome is uniquely defined given the trajectory of the agents and in the simulation, and we can compute the probability of collision. Now, to kind of these policies, right? As mentioned before, these are kind of the hard part to address. So we have all kinds of policies implemented. For example, we have constant speed agents. Those essentially they have a starting condition, and they just follow their starting condition without, without ever changing their acceleration. So the change in acceleration is 0. No, the acceleration itself is 0. Or we can have some heuristic based agents. For example, a start-stop agent. That is an agent that just avoid frontal collision by decelerate when it's too close to the self-driving car, or they accelerate when they observe that the self-driving car is moving too fast. And we obviously have more sophisticated agents than those. We have kind of imitation learned agents. We also have reinforcement learned agents. And actually at my talk at CVPR earlier this year, I talked about the reinforcement learned agents that we've created. So you can imagine that we have a set of all kinds of policies covering the space of driving policies to represent other agents. Now, we can also condition the policies on features, human-defined features, like aggressiveness. Right? We might have a policy that is fairly aggressive, that runs over the red line, that cut in aggressively. We also have agents that are slow to react. So usually we have we know the distribution of reactivity time, and essentially we can create agents and policies along that entire axis. So we have some agents that we represent people with some cognitive slowness. Then we need to account for those cases as well. Finally, we parameterize our policies using these dimensions like aggressiveness or as reactivity, and then we can sweep through the various levels of aggressiveness and reactive time, and that gives us a strong coverage of everything that we need to know in this. That's a more extensive evaluation strategy. Now, once you have kind of starting conditions once you have your starting conditions and your policies, and now the question is, what is the likelihood of this particular state happening? So we need to estimate. So the overall probability consists of, so how we are thinking about it, it consists of three different probabilities. One is the initial condition, like given without disregarding the policies, just looking at kind of one state at one frame, what is the likelihood of this this traffic situation happening? The second one is perception probability. So in this particular case, we are essentially skipping, marking the entire perception stack, but we know the perception is not perfect. For one, it can't really see behind occlusions, right? And we can treat perception as a generative model, so it gets the ground truth kind of initial condition, and then with certain probability will generate an alternative set, like a mocked perception of the scene that will be fed to the self-driving car. Finally, there's a policy probability, which describes the probability of the policy being taken by the other agents, right? So a lot of, for example, if you take a nominal agent, which is an agent that's fairly polite, that's an average driver, then the probability is fairly high. But you also need to model the long tail, and those are policies with a much lower probability. So then you have to multiply all these probabilities together. Now, in terms of initial condition, for some situations, we can even model it, using the 1D simplification that we had before. For example, the cut-in for a simulation of the cut-in scenario, or a simulation of the right turn agent scenario. Essentially, this green car is going to, in the eyes of the self-driving car, the green car will just pop up, anywhere along this 1D dimension. And in the right turn agent scenario, it's a similar process. So basically, because in the right turn agent simulation, they can then still disappear if they're trying to kind of just go across us, right? They enter the frame and then disappear. And we can estimate the probability of the distribution over where these agents might enter and enter in our path by just looking at the millions of miles that we've already driven in San Francisco. And we can further make the estimates more accurate by conditioning them on the agent types. For example, you have a vehicle, you have a bicycle, you have an emergency vehicle, that's the EMV, so they are usually more aggressive than they should be. We can also condition the distribution according to other things like maneuver time and manual defined maneuver types or or a particular traffic control. So in the end, we can condition on kind of many dimensions, like the three that we've outlined here. Then we can look at all the historic data, which can give us some kind of a probability figure of what can happen. Yeah, the second type of probability is a kind of perception probability. So if we model perception as a generative model, because we are not running the full perception here, and essentially in the Cartesian simulation now, the agent, the self-driving car might not see the green car for a very long time, and we can also model fog this way. For example, there is 10% chance of fog, which results in perception not recognizing this car for like 50% of the time. So these are all statistics, low-level statistics that we can draw from our past history, and that gives us an estimate of the likelihood or probability of these things from happening. So again, I don't need to tell you more what perception probability means, because we've all been there. Here we have a narrow street and we have a car like turning, and we don't see the car until the very end, and therefore you can't really feed the ground truth, because we have the ground truth car here. In the ground truth, we know the car is coming, but we can't just feed all that information to the self-driving car stack, because otherwise it would have behaved otherwise. So it would not have been very realistic. Now, to policy probabilities, actually the more complicated things. So imagine we have a set of policies for all the other agents, and we need to figure out, okay, how likely are these policies being executed? So here we can again rely a bit on the historical data, and for example, like a policy that tries to being very aggressive and just trail us by like 1 meter, and we then look at our past data, and we look at, okay, what is like, how often does it happen that an agent trail us like 1 meter, just right behind us? So again, this is just with sufficient parameterization that we could get a certain level of probability for these policies, and just with the initial condition probability, we can further break it down by different maneuvers. For example, we can break the policy down, like for example, when the self-driving car is making an unprotected left turn, and how what is the likelihood of that agent executing a particular policy. And again, we can break it down by agent type, traffic control, maneuver type, and different positioning. All right, so we've talked a lot about kind of log simulation. So these are ones where we use previously observed scenarios and to generate the distribution over the possibilities, and we can now compute, right? We know the state, we can roll out the state. That gives us a P collision, and we can aggregate them using the probability that we just talked about. But this way, a lot of times we don't. We essentially make sure that the self-driving car is doing well, like in this space that's covered by logs. So essentially, how I see it, it's like interpolation between different scenarios. So another interesting thought here is that we not only use logged scenarios for testing in simulation, but we can use kind of more adversarial type of scenarios. And how I think about it, this is like extrapolation. So we are going into the unknowns. The downside is that we don't know what is the probability of these events happening, because they're kind of far away from the distribution we've observed. but they can potentially find kind of weaknesses that were unknown to us before. So this is something I already showed at ICRA a few months back. So essentially, this is again a toy example. It's a 1D toy example of 3 cars driving in parallel. You have the orange car, you have the blue cars, and we can essentially train a model. If you want to know more about this work, I think my ICRA talk is somewhere on YouTube. So essentially, we can train a model that then we can query the model and say, okay, hey, here is the scenario. Let's make this scenario worse with respect to the policy of the self-driving car. So you can see that if we do that, and we can do it incrementally as well. So we can say, okay, make it a little bit worse and make it tremendously worse. So you can see that in the end, the blue cars learned to just cut in right in front of us and immediately press brake. And in some of the cases, we did hit them. But again, this is very simulated, a simulated toy example. Okay, open questions regarding simulation, testing in simulation. So I think, that there's a rabbit hole in simulation, which is you can always try to make it more and more realistic. So it's kind of endless. It's kind of, you can endlessly make simulation more and more realistic. The question is, what is the minimal useful parameterization that still gives you some signal with your simulation, that you can still catch problems in your self-driving car stack without going too deep? And how do we model long tails? How do we do sampling efficiently, so we don't always sample kind of states where we are doing well? It's very likely, but we're doing really well. Then we need to, but even for training some of these, as I mentioned, for probability estimates, we still look back into mileage that we've driven, and how can we reduce that? How can we reduce our on-road mileage while still being able to estimate probabilities as well? And finally, metrics is still a big question. So previously we just talked about probability of collision, but it's obviously not the only thing we're looking at. A lot of other things are like comfort, like near collisions, and so on, and obvious collision severity. So collision is not simply binary. If I may summarize today's talk, we highlighted challenges in both mapping and testing simulation. We deep dive into offline maps for self-driving car, what they are, how they are applied, what are some of the remaining challenges. We talk about construction zones, which is a fairly challenging, interesting problem. And we talk about a framework for testing the self-driving car in simulation. These only represent a small fraction of the ongoing research and engineering works at Cruise today. And if you'd like to learn more, please apply to Cruise. We're still hiring, and we are still looking for wonderful people like yourself. Thank you.
Thank you very much for your talk, and thank you for connecting with us so late in the night in San Francisco. So I currently don't see a question from the audience, but I would like to ask a question. In the beginning you talked about mapping, and so it seems that at Cruise you are heavily relying on maps, and so what I would be wondering, if there are efforts that you basically want to reduce the amount of maps which you are using, or do you say it's just not a problem to maintain them for the applications you want to solve at Cruise?
First, there's some echo, it seems. We can turn off some echo. Be great. But you can hear me, right?
Yeah, we can hear you well, yes.
Perfect. So, I think honestly, for San Francisco, even for a few cities, the way we have been, as I mentioned, we're doing a lot of auto labelings anyway. So, resources required to update, to keep the maps up to date for a city like San Francisco, and maybe even several other cities. It is fine. It's probably scalable in that sense. But I believe, I mean, this is just my personal opinion. If we want to really scale to like every major city plus suburbs plus rural areas, the way we are doing this kind of pre-processed offline maps is probably not the best idea. So, and as I mentioned, we have work that tries to reduce the reliance on the maps. And as I also mentioned in the talk earlier, we do see a future where we don't need map elements. So that this many map-like elements, as we discussed earlier, and also a world where we can potentially rely on some more implicit kind of geographic representation coming straight from perception stack.
Okay, perfect. Thank you. Are there questions from the audience? Yes.
Maybe a question. So about the precision of the object detection, you mentioned the earlier in the presentation that there is need to start something
Yeah. So I think I'm going to repeat the question. And so about how accurate is your precision for object detection? Yeah, what's the current state of the art in accuracy for object detection? Or
what kind of objects are we talking about?
The object that you mentioned that are needed to autonomous driving, you said that they need to centimeter level object detection, and the state of the art is not there yet. So whether it is what
if you so the question is that you said in your talk there is a need for centimeter accurate object detection, and the state of the art now doesn't seem to be there. So, or in the end, of course, it also depends on the sensors, right, which you are using to achieve this accuracy. And maybe
so we are talking about like maps, as we that was coming from the talk.
Yes.
So I think the requirement, as mentioned, the requirement for these maps is, like we were talking about centimeters. Now, how well can we do it with auto labels? I think for a lot of cases we can do them pretty well already. But obviously we had to change the architecture a little bit. Like if you just use like typical localization and pillar approaches that are used for object detection for cars and pedestrians, it's not going to cut it straight. Because usually the voxels are fairly large, and you lose a lot of in terms of precision, you can't get the precision that you need. So there are like particular tricks that can be applied, starting from just making the voxels denser, right? Because you can afford you are doing something offline, you are handling really a lot more points than your onboard system anyway. But there are other things that you can do as well. So I think the question, it depends. I mean, I can't give you like a number between 0 and 1. That's because it really depends on the scenario. It depends on the map element we're talking about. But there's certainly room for improvements.
Okay, thanks.
I would have another.
Is it?
I would have another question.
Yeah, there is another question from Patrick actually.
Yeah, I would be interested in you talking about parameterization of driving policies. So we have different policies. Have you been looking into modeling them with kind of inverse reinforcement learning techniques, or is it still kind of just combination of MLAD to learn from expert demonstrations?
I'm not. I think I have to repeat the question. So, before in simulation, you talked about different driving policies which you can parameterize, and so the question was a bit if you are using something like inverse reinforcement learning to learn those policies, basically to model those policies, or how are you solving this problem?
So there are policies that are fairly heuristic. As you mentioned, policies are literally constant speed. And there are policies that are manually designed as a stop drive policy that I mentioned earlier. So the question is like when we, I mean, how to, sorry, I don't understand the question. Can you just quickly repeat?
Yeah, but no, but I think in general, if you say the in general, if you say the policies are heuristic, I think that's more or less answering the question, right? So you are not trying to get the policies from real driver behavior. So it's more a heuristic
No,
model.
we are. So there is a lot of imitation learned policies, and that's by just observing how other people drive. And then I think with reinforcement learning, it's I mean usually that's used to model your own policy. If you use reinforcement learning to model other people's policies, actually, I'm not sure how to do it because you need a word model to train the RL policy. And if you just do self-play, they'll optimize themselves and you won't get something. In the end, you need to basically model how other agents are going to drive. And you can't just model them with self-play because they will develop something that's nowhere near what is really realistic in the world. So usually we have imitation learned policies, we have adversarial policies. Those are RL trained, but those are, because they are kind of adversarial. The targets have been clear. But yeah.
Yeah, no, great. I think that answers the question very well. Yeah, and then thank you very much again. We are a bit ahead of the time, so yeah, thank you. I think there would be more other questions, but I think we have to move on. Yeah, thanks again.
Thank you so much.
And yeah, thank you very much for your talk. And then we're gonna move on to our next speaker.